Hello, everyone, and welcome. And thank you for coming to my talk on Java security evolution, out with the old, in with the new. A little bit about myself. I'm currently tech lead of the security libraries team at Oracle, and I'm also the OpenJDK security group lead. In the past, I've been specification lead of JSR 55 and 105. More recently, I've authored or co-authored several JEPs, including 411, Deprecate the Security Manager for Removal, and 486, Permanently Disable the Security Manager. I'm also on social media, on Blue Sky and Mastodon, and I also blog about Java security features every time we come out with a new JDK release. So it's a good way to keep up with what the new features in each JDK release. However, I've not done the blog for JDK 24 yet, but I hope to have that out in the next week or two. So the goal of my talk today is for you to understand why and how we continuously evolve the security features of the Java platform. And here's my agenda. I'm going to start off with just a brief overview of what we do in the OpenJDK security group, and then I'm going to talk about Java security evolution and why it's important. I'll then talk about post-quantum cryptography and the enhancements that we've recently added to the JDK to help protect your applications against the looming threat of quantum computers. I'll discuss the disabling of the security manager in JDK 24, which I'm sure you've heard about in the keynotes earlier this week. I'll explain why we disabled it and the impact that it might have on your applications. I'll talk about a few recent enhancements and some future work on the horizon, and then hopefully we'll have about 5 minutes or so for Q&A at the end. Okay, so OpenJDK Security Group, we are developers who work on the design, implementation, and maintenance of Java security library components. These are APIs and implementations in various security areas such as cryptography, public key infrastructure, secure communication, and authentication. And we implement numerous standard algorithms and protocols, things like SHA-256 message digests, Edwards curve digital signatures, AES ciphers, PKCS12 key stores, TLS 1.3, and many, many more. For more information, you can check out the security group page. It'll give you a little bit of an overview of those areas, and it also explain how our source code is laid out. You can also subscribe to the mailing list. That's more of a daily activity of what our developers are working on and the features that are going into the next release. But if you're just interested in an overall programming guide, the Security Developers Guide is an excellent reference. Okay, I want to start off by talking about Java security evolution and why it's important. How many people here today work on security technology? Just a raise of hands. So a few of you, okay. Well, I'm going to bet that those of you that work on security technology and many of you that don't know that security is a very dynamic science. So over time, cryptographic algorithms and protocols inevitably weaken. But thankfully, stronger algorithms and protocols are continuously being created to replace those older and weaker ones. And then there's quantum computers, which are predicted to eventually break the security of widely deployed public key-based algorithms, which are used to secure communications on the internet today. So the bottom line is that change is constant in the security world. And the Java platform must be agile and adapt to this changing landscape by continuously deprecating old and broken algorithms and bringing in new and stronger ones to replace them. So this is a table created by American computer scientist Valerie Aurora, and it shows the lifetime of popular cryptographic hashes over the past 30 years or so. Although it ends in 2017, it illustrates the dynamic nature of the cryptographic landscape. So the table shows several hash algorithms that have been created over those years, where green means the algorithm is still strong and red means it's very broken. And as you can see, several significant hash algorithms have been broken in the past 30 years, including MD2, MD4, MD5, and JavaOne. SHA-2 and SHA-3 are still considered secure, but even SHA-2 has shown some minor weaknesses. Now, I could create another table for encryption algorithms or different types of cryptographic functions, and you would see a similar pattern of many algorithms weakening over time and then stronger ones replacing them. So there are several principles that guide us in ensuring that Java continues to be a secure platform for you to develop and run your applications on. The first principle is that we strive to make our configuration secure by default. And this means making our API and tool defaults strong and changing them over time as the landscape evolves. It also means disabling broken or weak algorithms and protocols, especially in network-based technologies where an attacker might be able to leverage a weak algorithm over the network. So we disable weak and broken algorithms in certificate chain validation, TLS, signed jars, Kerberos, and XML signature. Our second principle is to provide a solid cryptographic foundation. We want to continue to bring in and implement new and modern and strong cryptographic algorithms and protocols. And we'll also design and deliver new APIs as needed. In JDK 21, we added the KEM API, which stands for Key Encapsulation Mechanism. And in JDK 24, we've added a preview API for KDF, which stands for Key Derivation Function. Both of these APIs are going to be important building blocks for our subsequent post-quantum cryptographic work, and I'll go into that in a little bit more detail later. Our final principle is we want to provide tools that help you monitor and detect security risks and issues. Both of our tools, KeyTool and JarSigner, will emit warnings if you're using weak algorithms. And we've also enhanced Java Flight Recorder to log crypto events about the cryptographic algorithms your applications are using, which you can then use to detect issues in your applications. How many people here have heard about the cryptographic roadmap? Just a raise of hands. Oh, okay, phew, that's really good, that's great. So the cryptographic roadmap is, and the URL is right at the top, it's a website that we use to announce in advance security changes to currently supported Oracle JDK releases. So why is this important? Well, let's take a look at the Oracle Java SE support roadmap. One of the things you'll notice, JDK 8 was released in 2014 and expected to be supported to 2030 or later. That's 16 years or more, which can certainly outlast the lifespan of many cryptographic algorithms and protocols. So some of the algorithms that were released in 2014 may not be secure in 2030. So we want you to be able to not just rely on the latest feature release, but all the releases that we support for developing and running your applications securely. Now, all of the changes on the cryptographic roadmap first go into a feature release, such as JDK 24, and then they're backported. And they're also typically backported to OpenJDK update releases. So what you see on this roadmap is a pretty good indication of what other vendors will also do in their JDK releases. But obviously, you should check with them on the targeted date and targeted releases, as they could be different. So every one of these changes is designed to improve security in some fashion, but they sometimes have a little bit of compatibility risk. So the other advantage of the cryptographic roadmap is you get advance notice of the changes, a minimum of 3 months, but sometimes up to a year or 2. And most of the time, we're able to provide testing instructions. So you can try out the change before it takes effect to see your applications might be affected. So this is a snapshot of the planned changes table in today's roadmap. And I just want to go quickly through the different columns. The first column is the date that the action is targeted to. The second column is the releases that it is targeted to. And the third column is the algorithm or protocol that is affected. And the fourth column is a brief description of the action or change that is going to be made. The next column is the additional information, which points to more information about the change, including testing instructions. And finally, there's a change log, noting any changes since the action was announced. And this is an example of the additional information for disabling TLS RSA cipher suites. So as you can see, we give a little bit of more reasons. TLS RSA cipher suites do not preserve forward secrecy and are not commonly used. And then we provide testing instructions for you to try it out. So if you haven't been aware of the cryptographic roadmap, I highly encourage you to check it out, monitor it over time. It's give you a good idea of all the changes we're making to improve the security, and in most cases, we provide testing instructions as well. Okay, so wait, what are we going to do about quantum computers? So unlike traditional computers that store bits as 0 or 1, quantum computers are different. They use qubits, which can be both 0 or 1 at the same time with certain probabilities. This fundamental difference allows quantum computers to perform calculations that traditional computers could never even imagine. In 1994, American mathematician Peter Shor developed a quantum computing algorithm that can efficiently factor large integers and solve the discrete logarithm problem in polynomial time. This fundamental breakthrough meant that all mainstream asymmetric or public key-based cryptographic algorithms today, including RSA and all flavors of Diffie-Hellman, will be vulnerable once a cryptographically relevant quantum computer, or CRQC, can be developed. Now, experts have different opinions, but they predict that such a CRQC can be developed within the next 10 to 30 years. The solution to this threat is called post-quantum cryptography, or PQC, also sometimes called quantum-safe cryptography or quantum-resistant cryptography. So while 10 to 30 years might seem far off, many security experts say we have to prepare now for the arrival of quantum computers. If you're familiar with the TLS handshake, the key exchange step establishes a secret key that is then used to encrypt communications between two parties. That key exchange step is based on public key cryptography. So if an attacker can now gather key exchange messages and the encrypted communication data now, they could potentially decrypt them in the future when a CRQC becomes available. This is called harvest now, decrypt later. And because of this risk, many people believe early adoption of PQC key exchange algorithms rather than digital signature algorithms is crucial. The good news is that we've already started on this PQC journey in the Java platform. We've added 3 core PQC algorithms, and I'll go through each of them in a little bit more detail. The first is latent Macaulay signatures, also called HSS/LMS. LMS is a stateful hash-based signature scheme defined in RFC 8554. And it's believed that this algorithm will not be broken by a CRQC. It's also an approved quantum-resistant signature algorithm for CNSA 2.0, which stands for the Commercial National Security Suite. And that's a set of quantum-resistant algorithms approved for US national security systems. Now, it does require careful state management. And so it's really more suitable for signing artifacts with long lifetimes, such as firmware. In Java 21, we've added new key factory and signature implementations for LMS. The key factory, however, only operates on public keys, and the signature only covers the verification part. Because the signing requires careful state management, we don't include an implementation that supports signing or key pair generation. However, you can use a third-party provider that plugs into the JCE APIs. And we've also added support in Java 22 for jar signer and key tool support. So jar signer supports verifying jars signed with HSS LMS. Signing is also supported, but again, requires a third-party JC provider. Key tool supports generating LMS key pairs, but again, you need a third-party JC provider for that. The second algorithm that we've added is called MLChem, and this is a quantum-resistant, lattice-based key encapsulation mechanism specified in FIPS 203. It was defined in JEP 496 and delivered in Java 24. For MLChem, we've added new key pair generator, key factory, and chem implementations. The chem implementation is based on the chem API that was introduced in Java 21 and also later backported to Java 17. For MLChem, we support 3 parameter sets in increasing security strength: MLChem 512, MLChem 768, and MLChem 1024. If you're not familiar with chem, it's a fairly new crypto mechanism which uses public key cryptography to establish a shared secret key between 2 parties, a sender and a receiver. In chem, the sender uses the receiver's public key to generate a secret key and a ciphertext called a key encapsulation message. It sends that key encapsulation message to the receiver, which then uses its private key to decapsulate the message and obtain the same secret key. And then they can start encrypted communications with each other. In Java 24, we've also added support to key tool. It can generate MLChem key pairs and certificates. However, since MLChem is not a signature algorithm, the certificates must be signed with a different algorithm. So you could use RSA, or you could use MLDSA, which I'll talk about next. So the other PQC algorithm that we've added in Java 24 is MLDSA. And MLDSA is a quantum-resistant, also based on lattices, but this time it's a signature algorithm, and it's specified in FIPS 204. MLDSA was defined in JEP 497 and delivered in Java 24. And we've added new key pair generator, key factory, and signature implementations. And we support 3 parameter sets in increasing strength: MLDSA 44, MLDSA 65, and MLDSA 87. And you can use key tool to generate MLDSA key pairs and certificates. So to summarize, as of Java 24, we support 3 core quantum-resistant algorithms: HSS LMS, MLChem, and MLDSA. We've also added 2 new important building block APIs, CHEM and KDF. And we're going to build on that. Future JDK releases will be incorporating more PQC support in the higher layers, especially in TLS. I'll talk a little bit about the TLS layer later and TLS hybrid key exchange. So I'm going to switch gears now and talk a little bit about something different, the security threat landscape. So as technology changes, the security threat landscape can also change over time. New threats can emerge as technology changes. One example is quantum computers, which I've already discussed, and I've showed how we are adapting our technology to counteract this new threat. Current threats may also diminish in severity, or in some cases disappear entirely. One example that affects the Java platform is Java applet attacks. These used to be a significant threat for the Java platform. But since applets have been deprecated and browsers have removed support for applets, the threat of Java applet attacks has essentially disappeared. So that leads into my next topic, which is about the deprecation of the security manager. The security manager was originally created to defend against Java applet attacks, but it's had diminishing importance over the last few years. I'm going to explain why we disabled the security manager, and then I'm going to talk about the effects it might have on your application and the steps you can take to determine that. Okay, say hello to Dr. Deprecator. Is Dr. Deprecator in the house? No, he's not here. Okay, oh well. So there are many reasons why we deprecated the security manager. They're more fully explained in JEP 4.11, but I'm going to go over a few of the more significant ones. So as I previously discussed, one of the primary use cases for the security manager was as a sandbox for remote, untrusted applets. Now, applets were all the rage in the early releases of Java, and they really helped make Java popular. But by JDK 17, the threat of remote code had receded quite a bit. The applet API was deprecated in Java 9, and then deprecated for removal, I believe, in Java 17. Java plugin was removed from Oracle's JDK 11. That was the main mechanism that you could use to run applets. And furthermore, we had advised users not to run untrusted code. The security manager has always been very hard to configure and use as well. If you had a complex application that used a lot of different libraries, not only was it hard to determine all the permissions needed by those libraries, but those libraries ideally had to be developed with the security manager in mind and make the proper API calls. And this just didn't happen in practice, or it happened rarely. And so you ended up with awkward workarounds, in the worst case, granting all permission to code, which obviously heavily diluted the value of the security manager. The security manager is also really, really expensive to maintain within the JDK platform group. Even though applets were deprecated, we still had to support the sandbox and guarantee its security. It's a fundamental feature of the security manager. And this required hundreds of permission checks and privilege blocks throughout the JDK source code, all of which had to be audited and carefully reviewed for security issues. And then finally, alternative mechanisms had emerged over the years, things like containers and hypervisors that provided similar sandbox features. And although the security manager was sometimes used on the server side as a defense in depth mechanism, it never really gained much traction. A few reasons for that. Sometimes it was performance. Users were unwilling to take the additional bit of performance hit of enabling the security manager. But often it was because of the same usability and configuration issues that I mentioned previously. So in JDK 17, or Java 17, we announced that we were deprecating the security manager for removal. And that was defined in JEP 4.11. And this was more than just the JavaLang security manager API. This included a bunch of related classes and methods, all which are part of the security manager machinery. We also changed the JVM so that a warning was emitted at startup or at runtime, and it basically said the security manager is deprecated and it will eventually be removed. And we also made it clear that we were not going to replace the security manager. In Java 24, we've taken the next major step and we've permanently disabled the security manager. It is no longer possible to enable a security manager. You will get an error or an exception if you try to enable it at startup. If you try to dynamically set it at runtime, it will throw, the system set security manager will throw an unsupported operation exception. The security manager APIs do remain. However, they've been degraded to be essentially non-functional. And I'll go into that in a little bit more detail in the next few slides. At some point in the future, we will be actually removing the security manager API. This may happen over a few different releases, but the details are TBD at this point. So how do I know if I'm using the security manager? There's a couple of different ways you can find out. You can check your scripts or documentation for security manager references, see if it's starting on the command line with the java.security.manager system property. You can run your application on JDK 17 through 23 and look for those deprecation warnings warning you that the security manager is disabled and will be removed in a future release. You can also run the application on JDK 17 through 23 with the command line option Java Security Manager equals disallow. If your application is dynamically setting a security manager by calling system set security manager, it will throw an unsupported operation exception. So you'll know somewhere in your code that someone is setting a security manager. Or you can use the handy JDepr scan tool and scan for uses of deprecated security manager APIs. So in Java 24, if you try to enable or allow a security manager on the command line, you'll get an error saying a command line option has attempted to allow or enable the security manager. Enabling a security manager is not supported. Or if your application tries to dynamically set it by calling system set security manager, you'll get an unsupported operation exception with a message saying setting a security manager is not supported. This slide is about what we have done to preserve compatibility with some libraries that took the time to support the security manager. So libraries supporting the security manager typically use one or two common coding patterns. First, for checking permissions, they first check if the security manager is enabled, and if it returns non-null, then it calls the check permission method on that object with the permission that it wants to check. Or if they want to assert asserted privileges, they wrap the operation that they want to run as privileged and pass that to access controller do privileged. Both of these methods will behave the same as in previous JDK releases as if a security manager was not running. So system get security manager will always return null, and access controller do privileged will execute the action immediately. The benefit here is it benefits libraries that support the security manager. They don't have to be recompiled. They'll continue to work. These calls to the APIs will continue to work in Java 24 and in previous JDKs, and they have more time to remove the code when they are ready. We think that there are a much smaller number of applications that use advanced parts of the security manager API. Things like calling access controller check permission to check permissions directly, or setting their own custom policy implementation. These APIs, among others, have been degraded to either throw exceptions or provide an execution environment that disallows access to all resources by default. For these APIs, we wanted to make sure that we failed safe. We didn't want to pass silently. That could mean that an operation that failed previously with the security manager would now silently pass, and that could be considered a security issue. But we believe that the use of these APIs is much rarer, so the compatibility risk should be low. The security manager also impacted JAS, which stands for the Java Authentication and Authorization Service. How many people have heard of JAS or use it in their applications? Okay, a few of you. So JAS basically consists of two parts. The first part is an authentication API, which allows you to plug in different login mechanisms which authenticate principals. And the credentials of those principals are then injected into a subject object. And later, that subject object can be used for authorization decisions. One of those methods is called subject-get-subject. And in Java 24, this has been changed to always throw unsupported operation exception. This API was particularly problematic because it has a direct dependency on the access control context API, which is deprecated for removal. The good news is that we knew about this several releases ago, and so we added replacement APIs in Java 18. So if you're using that method, you must replace calls to subject-get-subject with subject.current, and it is functionally equivalent for the most part. You should also replace calls to subject.doAs with the replacement API subject-callas. Subject-doAs will still work. It's basically just calling subject-callas under the hood. But it's also deprecated for removal, so you should transfer to the replacement API sooner rather than later. These two new APIs used scoped values in the implementation, which provides similar features as the access control context did. So I want to mention a few other significant recent enhancements which I think are worth mentioning. In JDK 22, we added a new security category to the Java-X show settings option. And there are sub-options for properties, providers, and TLS sub-options. The properties will show all the values of your security properties. The providers will show all the algorithms that are supported by your installed JCE providers. And the TLS sub-option will show the enabled protocols and cipher suites that are in use. So here's an example of using the XShow settings with the TLS sub-option. As you can see, it shows the enabled protocols, 1.3 and 1.2. However, it doesn't show 1.1, 1.0, or SSL v3. Does anyone know why?
Right.
And take a guess? Right, they're disabled by default because they're no longer recommended for use and have security issues. And then it shows a list of all the enabled cipher suites. In JDK 23, we added a new key store for Mac OS root certificates called keychain store-root. So now we support two native Mac OS key stores, one called keychain store, which contains the private keys and certificates for the user, and keychain store root, which contains the root certificates on Mac OS. This can come in handy if, for example, you're running an application on Mac OS and your TLS connection fails. It might be because we don't include a root cert in the JDK that the Mac OS platform does. So in that case, you can try setting the JavaXNet SSL trust store type system property to keychain store root to see if it resolves the issue. Finally, in Java 24, we've added a new preview API for the key derivation function. And this is a new API for deriving keys from key material and other data. And we include an implementation of HKDF, which stands for HMAC-based extract and expand key derivation function. It's quite a mouthful. This is going to be really useful for subsequent post-quantum cryptography work, and it's also going to be useful for stronger password key derivation algorithms that we're working on, such as Argon 2. I encourage you to check out that JEP. Let us know what you think about the API and provide feedback as we still have a chance to make changes. So finally, I'd like to mention some potential future work on the horizon. We are working on a new API for PEM. PEM is a widely used format to transfer different kinds of security data, certificates, public keys, CRLs, you name it. When we launched a JC survey a few years ago, this was one of the top requested issues by users in the community. So we're going to do it. We have a JEP draft out there. And again, I encourage you, this is the time to give us feedback. You can check out the API, see if it satisfies your needs. We're also going to be working on additional PQC support. Two things on the horizon are TLS hybrid key exchange. This is a new key exchange mechanism being standardized within the IETF and allows PQC algorithms to be negotiated along with classical algorithms in a hybrid approach. And it provides additional security should one of those algorithms be compromised. Some of the PQC algorithms are quite new, and they haven't had a lot of exposure. There may be security issues in the future. The other main effort in the PQC area we're working on is called hybrid public key encryption, and that's a new standard scheme for encrypting data with public keys and can also use quantum-resistant algorithms. And finally, our friends at Red Hat have proposed a new feature called Security Providers Filter. And this is basically a new security property that allows you to filter the mechanisms that are supported by security providers. So you could decide that I don't want any provider to advertise or use MD5, and it would just be completely shut off. Again, there's a JEP draft there. I encourage you to check it out, read it, and let us know if you have any comments. Okay, so to conclude, I hope you have a better understanding of how we evolve security and why it is a continuous and critical process. So we're going to continue to adapt Java security to meet the security needs of your applications by disabling weak algorithms and removing legacy features to reduce the attack surface, and by implementing new and stronger algorithms and strengthening the platform to withstand new threats. In other words, out with the old and in with the new. Thank you very much. And we have a little over 5 minutes for questions. So if you want to use the mics.
I was wondering if you could touch a little bit on performance of the built-in algorithms and whether they're able to use hardware optimizations. So we recently had an issue with an app that's on 17 and doing a lot of crypto that was slow, and we resolved it by plugging in Amazon's JCA implementation. So maybe things are different now, but I'm curious if that code is implemented in Java or if it's native, that sort of thing. Thank you.
Yes. So we've been doing a lot of work in intrinsics lately. I don't have performance numbers there, but we're able to, I'm not sure if this is answering your question, but we're able to get significant speed up on the architectures that we've added those intrinsics for. I'm not sure if you're storing your keys on hardware. Is that also something that you're, because for that, we support the PKCS11 provider, which is able to, the keys never leave via your hardware device, and that way you improve security that way.
I'm really glad to hear that the PEM format is coming. I'm just kind of curious, maybe, like, why did it take so long to get to this point?
It's a good question. We did support it a little bit. Like if you look at the certificate factory API, it can read the PEM format for certificates and CRLs, but we never expanded beyond that. And it's also a little bit of a different API for us. It's at a higher layer, and so we're just going through a little bit more of a design phase. But it's better late than never, right?